let's take a look at an example where we're going to apply a transformation to just the base function, y equals c to the x, or not c to the x, y equals 3 to the x. And we're going to transform it into a different function using some methods that you've learned in the past. Okay, so in this problem we're going to transform the base function, y equals 3 to the x. We're going to transform that to y equals 2 times 3 to the power of x minus 4. Okay, and before we do any transformations, either graphically or on a table, let's just identify what's happening here. Okay, what kind of transformations are taking place?
Vertical stretch by a factor of 2.
Okay, so this is the value a. Okay, so a equals 2, and that's a vertical stretch. My H's look like B's. And that doesn't even look like the word stretch. Blah. Stretch by a factor of 2. If I were to transform a point from my base function to my transformed function, what would that do to the coordinates of that point? Just that particular transformation. If I stretched it vertically by a factor of 2, what does that do to the coordinates? It doubles the y value, right? So that's going to be helpful when we go and transform some points. It doubles the y value. Okay, that's going to be important.
So can't you also put that as like y goes to 2y?
Say that again?
Or mapping notation, isn't that like y goes to 2y?
Yeah, if you want to do mapping notation, it'd be x. The generic point xy maps to x, comma 2y. Sure, you could say it like that.
Surprised I remember the name for
Yeah. Okay. This here is not a transformation, right? That 3, that's just the rate at which your thing is growing. What about up here? What's going on up here?
Moving to the right.
It's 4 to the right. This is h right here. Okay, so h is 4. I'll just make that, I'll make it green. Okay, so this guy right here, that's the value of h. So h is 4, which means I have a horizontal translation 4 units right. Okay, and if you want to use Joe's mapping notation, that would just be xy maps to x plus 4 y. Okay, so that affects solely the x coordinates. Good? Okay, so now what we're going to do is we're going to take a table of values. I give you some of the points on the curve y equals 3 to the x, and we're going to transform those points doing the stretch first and then the translation. And we're going to find out where those points are going to end up, and then we'll graph them. Okay? So the points that we have are -1 and a third. You don't have to write these out, they should be on your paper. 0, 1, 1, 3, 2, 9, and 3, 27. Okay, and the first transformation we're going to do is the vertical stretch, which is just this. So let's do that first. How does that affect these points?
Multiplies the y coordinates by 2.
Good, okay. So the first coordinate is going to become -1, 2 over 3, right? You double a third, you get 2/3. Okay, again, it only affects the y coordinate. Okay, the next point would be 0.
0, 1 still.
No, doubles the y coordinate.
0,
2. Next one,
1, 6.
1, 6. Good, now you got it. And 2, 18. And 3, 54. Yeah. Okay, so that's the first transformation. The other transformation that we had to do was a horizontal translation 4 units right. Okay, so now I'm taking these points that went through the first transformation and I'm going to transform those with this 4 units right transformation. Okay, so I bring -1 and 2/3 4 units right. What does it become?
4, 3.
3. And the y coordinate stays the same. Okay, so 3 2/3. Then I take the next point and I'm only adding 4 to the x. That's it. So it becomes 4 and 2, and then 5 and 6, 6 and 18, 7, right, 7, and 54. So this right column here, these are the points that I'm going to plot for my transformed function. Okay, those are the only ones I have to worry about for my final transformed function. And if you turn the page, look at that. Wow, the graph is right there. You don't have to draw it. It's even scaled properly. How convenient. Okay? If you're watching on YouTube, here is that graph.
Thank you, Mr.
How convenient. Okay, so let's point first the base function. Okay, we're going to point both the base function and the transform function. The base function is going to be easy to plot because we've got these black points. Okay, so -1 and 1/3. Let's plot that, which is going to be hard, but do our best. So -1 is about here, and going up 1/3, barely above the x-axis. Use a tiny point. Nope, that missed. There we go. Maybe a little high, but close enough.
10 though?
No, 10 is here. I want to go -1 over and 1/3 up for
So wouldn't it just be like
this point.
barely off the line though?
Barely off the line, yeah.
It's like hard to get close to the line with that dog.
Yeah, it's a stylus, man. It's hard. Don't hate. You got a pencil. Okay. Next point is, okay, we're going to do 0, 1, and then 1, 3. Okay, very tiny graph. 0, 1 is barely above where we just graphed. And then 1, 3. So that would be, man, this is still not good. Nope, do it again.
Oh, man.
That's better.
Oh, well, good job.
Huh? There we go. There we go. That's a nice one. Okay, and then we have, what else do we have? 2, 9, 3, 27. That'll be a little easier. So 2, 9 is just below 10, 3, 27. There we go. Okay, let's draw this. If you have a pencil, it's really easy. If you have a stylus, it sucks. Oh, I missed! No, I got my dot! It's like the most amusing part of math class is trying to watch me graph with a stylus. Yes, yes, yes. Good.
Echo is the best part.
The echo, yeah. Okay. Let's try now the green curve, okay? The transformed points. So 3 2/3 and 4 2. Okay. 3 2/3, which is not going to be very high. We'll say there. And what was the other one?
4, 2.
4 2, thank you. We'll go there. Next point.
5, 6.
We got 5 6, 6 18, 7 54. Hopefully I can remember all that. 5 6, 6 18, 7 54. Okay. Asymptote hasn't changed, so that still comes from infinity. And it starts growing. Boom. That was a nice one. There we go.